Okay, we've spent a couple of days looking at history of the atomic theory, so where this idea of the atom came from. We spent a little bit of time with the PhET build an atom simulation, so you should be familiar with some of the component parts of the atom. We're going to look a little deeper into that today, and so this is kind of the introductory lecture for Unit 2, which deals with atomic structure. Okay, first thing, you should already kind of know this stuff. By going through that PhET simulation, but you need to know what atoms are made up of. And so all atoms are made up of these same three subatomic particles, the electron, the proton, and the neutron. What you need to know, the electron, you notice we symbolize it with an E with a little minus sign above it. It is found orbiting the nucleus, so it's in orbitals, so another name is the electron cloud, so it's surrounding that center, the nucleus. Notice they have no mass. Okay, electrons are essentially massless. They do have mass, but man, it's so tiny, it is insignificant. It takes 2,000 electrons to equal the mass of either a proton or a neutron, and no atoms have that many electrons, so they essentially have no mass. Notice they have a -1 charge. The proton, symbolized here with just a plus sign, is found within the nucleus, so that tiny dense center in the core of the atom. They have a mass of 1 AMU. You'll notice at the bottom I mentioned that AMU stands for an atomic mass unit. They have a charge of 1 plus. And then finally, the last subatomic particle is the neutron. They are symbolized with a lowercase n. They're also found in the nucleus. They also have a mass of 1, but what's different, they have no charge. That's why they have their name, neutron. Neutrons are neutral, no charge. So these are the same three particles make up everything. And so, like I just mentioned, all matter is made up of those three subatomic particles. What makes them different is the number of particles or the number of each subatomic particle in each different element. So, gold atoms are made of the same thing as the oxygen atoms you're breathing in. Only thing that's different is the relative numbers of protons, neutrons, and electrons. The other kind of important thing with atoms and how they work, it's this real basic, simple principle that says if things have opposite charges, they attract one another. If they have like charges, they repel. Okay, and so here's just a model of an atom. This one happens to be helium. But if you look at this, you'll notice kind of the structure. Now, this is not to scale. Okay, so here on your computer screen, let's say that this thing is the size of a quarter. Okay, just to give you some idea, if this were drawn to scale and the nucleus was that large, about the size of a quarter there in your screen, those electrons would be over a half mile away. Okay, and in between there is nothing, it's empty space. So, kind of a weird deal. I'll probably give you guys a link that's called How Small is an Atom. I'll have you watch it and I'll show you kind of the relative size of things. It's kind of crazy. So anyway, here's the basic structure of an atom. You're going to note that here we have protons that are in here. These protons are pushing away on one another. They want to fly apart, but what they're being held together by are these neutrons. So those neutrons, their effect on the atom is holding the nucleus together. They exert this thing called the strong nuclear force. At the same time, you notice we have the electrons out here in orbits, and they're zipping around. Okay, they are attracted to the nucleus, but they can't reach the nucleus because they're moving so fast horizontally. Okay, but that's basically what matters, or what all matter is made up of, or these atoms. Tiny dense centers with nucleus, a lot of empty space in here, and then electrons zipping around. So that's basically how atoms are laid out. Okay, you will notice that I have shared with you this link. I'll probably share it again. So this is going to be, I'm going to give you guys your virtual periodic table. I'll also give you the digital copy just so you can look at this. I just want to point out a few things here. Any decent periodic table is going to have at least 3 pieces of information on there. They'll almost always have an atomic number listed on them. They're going to be a whole number. Okay. Usually, you're going to notice that periodic tables have keys, and it'll tell you what number is which on there somewhere. But the atomic number is usually going to be emphasized. It's going to be in either larger font type or bold or something. And you'll notice that it's always a whole number. Okay, the atomic number is equal to the number of protons in the nucleus of an atom. That's what defines what an element is. It's the number of protons. Oxygen, for example, always has 8. If it has 7, it's not oxygen, it's nitrogen. In this case, we have iron, which is 23. So the atomic number, not 23, 26. The atomic number is the identity of the element. So the number of protons tells you what element it is. Okay, you're going to notice up in the upper right-hand corner of this particular example, this is what's known as the average atomic mass. You will note that the mass is equal to the number of protons plus the number of neutrons. And that makes sense because, as you'll recall from a previous slide, only the protons and neutrons have mass. The electrons are massless, so they don't count. The other thing you'll notice is that almost every table will have a symbol representing elements, and they'll either be 1, 2, or 3 letters. The first letter is always capitalized. Any additional letters are lowercase. We're already kind of familiar with that from the first unit, but those are usually the minimum piece of information you're going to see on a table. Couple of other terms I want to throw out there. Okay, there's this idea of what are called isotopes. What an isotope is, by definition, they are atoms of the same element that have a different atomic mass because they have different numbers of neutrons. You're going to notice when we came back to this slide, if I said we added the protons and the neutrons, you might say, well, why is that a decimal number? Because you can't have fractional parts of protons or neutrons, you have to have whole ones. So why is it a decimal? Well, the reason why is because of these things, these isotopes, because they're elements, atoms of the same element, but their masses differ. And why do they differ? Because they have different numbers of neutrons. Okay, it can't be different numbers of protons, because if the proton number changed, that would be a different element. So this idea of a different number of neutrons is what makes this thing an isotope. It is important to note that all naturally occurring elements have at least 2 isotopes. Okay, and the other thing is kind of interesting. Isotopes are chemically identical. That means they form compounds with the same elements in the same ratio. But what is kind of interesting, and as you guys noticed when you were kind of playing around with that PhET simulation, when you had certain numbers of protons and neutrons, sometimes those nuclei became unstable. And what happens if something is unstable? It wants to reach stability. And how does it do that? It falls apart. They decay. They undergo what's called a radioactive decay. And so, isotopes. And I'll show you some stuff here with isotope notation. First thing, this one's called hyphen notation. So, for example, I'm speaking of a specific isotope here, carbon-14. Carbon-14 is actually an unstable radioactive isotope of carbon. It is one that decays and releases energy. Radiocarbon, I don't know if you've ever heard of radiocarbon dating. That's a technique that is used to determine the age of once living things, as long as it was alive within the last 30,000 years or so. You can't do it for dinosaurs and things, but if you find, anything that was living in the last 30,000 years and there's enough material there, you can do radiocarbon dating and determine approximately when that thing was alive. I don't know if you guys know this or not. You are radioactive. You have elements in your body that are decaying, and the majority, or the major one that's in your body, is carbon-14. Our body has a lot of carbon in it. We're mostly water. We got a ton of water in our bodies, but the other part, the cellular part that isn't water, it's largely carbon. And a certain percentage of those carbon atoms are carbon-14, which means we are unstable. We decay. So anyway, when you do hyphen notation, notice you put the element name, a hyphen, and then the mass of that specific isotope, so carbon-14. And so this is isotope notation. This is another way of doing it, to where you'll write the symbol, and then you put a superscript, so that means above the line of script to the left, that's going to be the atomic mass, and then you'll put the atomic number right below that. So here is another example of carbon-14. 14 is the mass. The atomic number is 6, because if it's carbon, it has to have 6 protons. The atomic number, the number of protons, are 6. Carbon is the element that has 6. That's just the way it is. So isotope notation. Okay, now the next thing, you'll notice it says in neutral atoms the number of protons and electrons are equal. Okay, so the positive and negative charges will cancel each other out. Nature loves things to be equal. They don't like having charges on things. If things get charges on them, they tend to try to lose them by forming compounds, by sticking to other atoms to lose them. So anyway, in neutral atoms, usually you're going to have the same number of protons and electrons. However, there are times when elements will either gain or lose electrons in order to try to become more stable. When they do that, they're called an ion. An ion is just a charged atom. It can be positive or negative. You'll notice there are two types of ions. We have things called a cation. A cation is a positive ion formed when an atom loses electrons. So as you lose negative things, you become positive. Okay, a cation. Here's another way you can think of that. A cat has paws, right? Like your house cat, their feet, you call them paws. Cats have paws. So a cation is a positive ion. How do you become positive? You lose negative things. And then the other type of ion is called an anion. An anion is a negative ion formed by an electron gaining electron. So as you pick up electrons, as you pick up negative things, you become negative. You become an anion. We're going to study, we'll have a whole unit about, chemical bonding, why atoms lose or gain electrons to become more stable. But just now, I want you to realize that they do. So these atoms will either sometimes gain, sometimes lose. And the way we're going to tell if they lose or gain is by looking at the periodic table. We're not going to worry about that just quite yet. Okay, the next thing I want to show you, I want to just run you through like an example. Okay, so in this case, you'll notice here we have a symbol, Fe. That's going to be iron. Okay, and as you guys recall, this number up here is the atomic mass for this particular element, or this isotope. This is the atomic number, is written down here. Anything written up here, if you see a number up here, this is a charge. Okay, and then down here later on, we're going to do this later on, but this is a counting number. It's just telling you how many atoms there are. Okay, but for right now, the ones we're focusing on are atomic mass, atomic number, and the charge, if any. Okay, what I'm going to do is I'm going to run you through something here pretty simple. I'm going to do a little chart here with protons, neutrons, and electrons. Okay, so if I ask you how many protons were in this particular atom, you would say there are 26. How do you know? Well, it's the atomic number. The atomic number and the number of protons are always the same. Okay, now you might say, okay, awesome. How do I find the number of neutrons? There's nothing here that says neutrons, but there is a way we can do this because we know that the mass number is equal to the number of protons plus the number of neutrons. Okay, well, we know the mass is here, so we have 56. And I just told you the protons are 26. And so what magic number plus 26 is 56? Well, how do you solve that? You have to subtract 26 from both sides. That cancels that, so what we end up with is x equals 30. There are 30 neutrons. And if you think about that, that makes sense. If I have 30 neutrons and 26 protons, 26 and 30 is 56. So that's how you determine the number of neutrons. For the electrons, notice this thing has a charge. Okay, if that charge were not there, the electrons and protons would be equal. The number of positives and negatives would cancel out. But because I have a charge here, and notice it's positive, well, if it's positive, am I going to have more protons or am I going to have more electrons? Well, it's going to be protons because it's positive. Okay, how many more? The answer is 2. So if this is 26, this has to be 24. And that's how you do this. I'm going to give you guys an opportunity to practice this today, and we'll get together. We'll practice some more tomorrow. But this is going to be a kind of a major part of the second unit exam, is being able to complete a chart like this. And so what I'm going to do is I'm going to look at a few things here. I've got pulled up here in the background, I've got ptable.com, and so we can look at some of these things. Okay, and so this first problem is asking about helium, and so here we have helium right here. Okay, so you're going to notice up here, this is the atomic number. This is an average atomic mass. Okay, we're not going to use the masses from the table, but the atomic numbers we most definitely can use. So if we're doing this and we have helium-4, we know right away that the atomic number is 2. We knew because we looked at the periodic table, and lo and behold, there's the atomic number. It is 2. Helium is 2. It's the only element. This is actually going to be the mass number. We're not going to use the 4.00 whatever it was. We're going to use this mass of this particular isotope, always a whole number. Okay. Now that we know this, if we know the atomic number is 2, protons have to be 2. It's the only thing it can be. Then you guys will recall that protons and neutrons, these two sum up to be the mass number. So what number plus 2 is 4? Well, there should be 2 neutrons. Notice there's nothing here indicating this thing has a charge, so we must assume the protons and the electrons are going to be equal. This is going to be 2 as well. So there's an example of how you would fill out one of these charts. Okay, let's do this one. Same thing. Atomic number 29. Well, we know the atomic number is 29. We know the protons must be 29. Okay, well, if I know the protons and the neutrons, if I sum these together, so if I do 29 and 36, let's see, that's a 15, carry the 1, 65 should be the mass of this particular isotope. Okay, there's nothing indicating this thing has a charge, so these two should be equal. Okay, so if I have 29 protons, I have 29 electrons. So I need to figure out what element this is. So I'm going to go back to my periodic table here. And so I need to look for number 29. Let's zoom out here a little bit. There it is, 29. And so it's going to be copper. Okay, we're not going to use this average mass. We're going to use the very specific mass, but that is the atomic number. So we can identify that element as being copper. So I'm going to say copper hyphen, and then the mass number 65. And that's how that works. Okay, let's look at this one. We have 8 protons. Well, if there are 8 protons, that means I have an atomic number 8. If the mass is 16, protons and neutrons add up to the mass. Well, what number plus 8 is 16? Or essentially, I'm asking you 16 minus 8. That is 8. Once again, no charge, so I'm going to say there are 8 neutrons. I need to look up on my periodic table for element 8 here. Lo and behold, there it is. Right here, oxygen, 8 protons. Okay, and so I'm going to put oxygen hyphen 16. If I were going to draw the symbol for this one, I would draw it like this. I would put the symbol O. The mass number comes up here, the atomic number goes here, and no charge because it doesn't have one. Likewise, let's go back and do these real quick too. So if I did copper 65, I'd put its symbol Cu. Mass number of 65, 29 for the atomic number, no charge because it's neutral. Let's go back and do that first one. Helium symbol is He, mass is 4, atomic number is 2, no charge. So that's that isotope notation. Okay, I'm going to do just a few. I'm going to skip over here, see if we can find some that are a little different. Keep going here a little bit. I know I have some different ones here in a minute. Here we go. Let's take a look at this guy. This one, okay, we see we have an atomic number of 30 because protons and atomic number are the same. So I'm going to put 30 here. What magic number for neutrons plus the 30 protons is going to give you a mass of 70? Well, there must be 40 of them. Okay, 30 and 40 is 70. If I look up this particular element, number 30, let's go back to our P table here. There's 30. It's right there. It's zinc. Okay, zinc is atomic number 30. Symbol is Zn. So let's say I'm going to put a symbol here, Zn. For the mass, we're going to do 70 for this particular one. Atomic number is 30. Now you'll notice I gave you the number of electrons, and the number of electrons were different than the proton number. I had 28 electrons, which are negative, and the protons obviously are positive. Okay, well, if I have 2 more positives than negatives, this ends up being 2 plus. If I name this thing, I'd call it zinc 70. I don't indicate the charge. Only in this type of notation do you indicate the charge. Let's do a couple more that are ions. Let's do maybe this one. Okay. Atomic number is 17 because I have 17 protons. Remember, protons and neutrons sum up to be the mass. What number plus 17 is 35? 18. And if I look at my periodic table for atomic number 17, there it is right here. It's chlorine, right? 17 is the atomic number. So I'm going to say, okay, symbol is Cl, 35 is its mass, 17 is its atomic number. Okay, I have 17 positives and 18 negatives. That means I have one more negative. It's -1. And so this is chlorine hyphen 35. Now note, here's another thing I want to show you. You sometimes will also see it written like this. If the charge is 1 plus or 1 minus, sometimes they only put the symbol. Okay, so in this case it's chloride anion. It has a -1. You just put a negative. Either one of these is common and acceptable. Okay, let's do, I tell you what, I'm going to do a random one here. Let's go back here. I'm going to go to a blank one. I'm going to give you some information. Maybe we'll do like 2 of them this way. Man, I had a lot of examples we skipped. Okay, let's look at this one. Let's say I give you something here like the symbol. Let's say I give you P, and this would be 15. And let's say this is 31, and I'm going to say 3 negative. Okay, well, without looking at anything, we know the mass is 31 because it's listed there. We know the atomic number is 15 because it's listed here, which tells me I have 15 protons. What number plus 15 is 31? 16 neutrons. Now notice I have a 3 negative, so that means I have 3 more electrons than protons. So if I have 15, that means this guy must be 18. If I look up and see what element this is, atomic number 15, here it is, phosphorus. Okay, symbol P. I'm going to say phosphorus hyphen 31. Okay, I'm going to do one more of these. I'm going to give you some to practice. Okay, let's say I give you something like this. Let's say I give you Al and 13 and 27 and 3 plus. Okay, well, from this I know that the mass is 27 because it's listed here. Atomic number is 13. It's listed down here, which is going to be the proton number. What number plus 13 is 27? Well, that's 14. Notice I have a 3 plus here. That means I have 3 more protons in the nucleus than electrons. So if there are 13, that means the electrons must be 10. I'm going to look at my periodic table here. Here's atomic number 13, aluminum. Aluminum hyphen 27. Okay, that should be enough practice for right now, or enough instruction. I'm going to give you a worksheet and have you guys attempt to practice some of these. All right.